All right, so this is our mean field variational inference. We partition latent variable Z into groups Z1 to Zm. Assume that the QZ, the approximating Z, is a product, is factorized, is a product of the marginal distributions over each group. Now let us try to derive. Recall the definition of the ELBO. So here is the definition of ELBO. ELBO is L of Q theta is integral over Q theta, integral over d theta Q theta log of the joint distribution between x and theta by Q theta. Of course, in our derivation, we will replace theta by Z. Okay, so LQ is integral QZ log of joint distribution by QZ. Now, we know that, of course, so first thing you do is that this joint distribution, this log of this ratio, you make log of the numerator minus the log of denominator. And what you do, you apply the mean field approximation. That is, you make Q as product over I equals to 1 to m Qi, where Qi is this individual Qi Zi. I'm dropping the Z actually. It's product of Qi Zi. So you split the ratio inside the log into log minus log. Replace Qz by product of Qi. Replace Q by product over Qi. I equal to 1 to m. So this is product over Qi, and this Qz is inside log. So product over Qi will be summation over the log Qi. Will be summation over log Qi. And now let us do one thing. This is the most critical step. I hope you can you hear me? I'm getting some message about network quality. Can you hear me?
Yes, sir. Yes,
okay,
sir.
Good. Thank you. So now, so this is simple. So LQ is integral product Q into log of the joint probability minus summation log of the Qi, the factorized Qi. Okay, so let us break down in our optimization problem into m steps. Each iteration of the optimization problem into m steps. In the first step, only change Qi. Only change, I think it's J here. Only you try to change your Qj so that this ELBO is maximized. Keep all other Qi fixed. So what I'm doing here is that I am in this product. I am this. Look at this product. Look at this product. I am splitting this product into Qj and all other i's not equal to j. Okay, so this product I am breaking up this way. Note that since this so I can do that actually. So this Qj is actually independent. I can do that. Okay. And let us look at this part. This is summation over all I. So what I do, I look at only Qj, because now I am changing Qj. Qj is the only variable here. All other Qi is constant now in my first step. So if all other I is constant, then I can write down this summation over I log of Qi into and there is a product Qi in front. So of this, if I only take Qj and bring it inside this integration, bring it inside only Qj into log. All other Qi are constant because they are not changing in this step. So log of all other qi is also constant, multiplied with those particular qi is also constant. So this second term, this into this, can be split up into only the qj. Note that this is only one step. In the next step, I'll write down a different expression for LQ. This is only the expression by varying qj, keeping all other qi constant. So this term, now I can get into two parts. Only one part is variable. The qj part is variable. Rest of the part are constant for this particular problem. Are constant. Okay. And this I can always do. This I can always do. So now define a new quantity called, this is a very important quantity. Okay. Let us define a new quantity called p hat. See, this new quantity is like this. It's like, see, our original, we are interested in this distribution pxz. Okay. P hat, and z has m parts. Z has m parts. Okay. So p hat x z is nothing but, rather, let me take a log of p hat x z is nothing but expectation with respect to all the q such that for all the qi such that I not equal to z. Say for example, you are doing for z2. You are doing for z2. What you do is you define the p hat for z2. Note that for every z I have a different p hat. P hat at z2 is like this. You take the expectation of full pxa. You take the expectation of full pxa. You take the expectation of full log of pxa, but the expectation with not with respect to entire q. See, let me elaborate a little bit on it. There are two things we can do. So this is pxz. I could have taken an expectation with respect to entire q onto m, all the parts of q of the quantity log of pxz. Instead, I do something else. I take the expectation with respect to q, but with the j1 dropped, the jth component dropped. I take the expectation. So whatever is inside the expectation is remains the same, but the distribution over which I take expectation is slightly different. How it is different? The jth factor in q is dropped. Jth factor in q is dropped. So it's basically a marginal of q with j removed. We remove j. It's a marginal over q with j removed. The jth factor removed. Okay. With respect to that marginal, I take a expectation of log likelihood of the joint distribution of x and z. All right. Plus actually what will happen is that since this p of xz is a distribution over full z, x and full z, and this q is a distribution over with j removed. So this is this expectation will have a different normalizing factor than the first expectation. So the normalizing factor of this expectation would be different. Expectation, you remember, there is a normalizing factor in the denominator that will be different because this q1 to m is no longer considered. But that will still be a constant. So what I do is that we say that this log of p hat is actually this expectation plus some constant term, plus some normalizing constant term. Okay, plus some normal. That's a kind of technical thing we need because we have changed the expectation over the distribution that one of the factor we have dropped. All right. But if this is my definition of log of p hat, but remember this is a very important thing. It's like if you recall our original bivariate Gaussian case, so it is like you are taking an expectation of log of the joint distribution with one of the coordinate dropped. With one, you are taking an expectation of the rest of the coordinates. So this is a very important point to be noted. Okay, so but if this is my definition, then this quantity, this quantity can be written as integral qj log of p curl xz, but x only zj and dzj. Okay. See what I told before. I want to change only the qj part, and in order to maximize LQ, keeping all other parts constant, right? So if we substitute this here, and this anyway we had only the jth part. Here also it becomes qj log of p hat x z j. This is only this part into derivative of zj. So again, if you combine it back, that means instead of this minus, I can write it as qj log of p hat xj p hat by qj. Okay, so this becomes this entire thing. If you, I'm no space to write it down, is nothing but the negative of the KL divergence between qj, that factor of q, and p hat. Just it's nothing. I brought this to the denominator, and that becomes the expression of KL divergence. Okay, so this LQ is now can be written as if you change only qj, keeping all other qi's fixed, assuming all other qi's to be constant, then LQ, the elbow bound, can be written at negative KL divergence between qj. We are now interested to get only qj, not other qi's. Okay. So let's talk about the distribution qj, between that distribution and p hat distribution. And what is p hat distribution? P hat distribution is we will soon explain what is p hat distribution is. P hat distribution has this property that log of p hat xj is nothing but expectation of log of pxj, where the expectation is taken with respect to q with the jth factor dropped. Naturally, so if you want to maximize this, you want to minimize the this KL divergence, because this is a constant and this is a negative here. You want to minimize you want to maximize this quantity. You want to maximize ELBO, so you want to minimize this KL divergence, and you know the KL divergence minimum value is 0 when qj equals p hat. The minimum KL divergence is 0 when qj equals p hat. Okay, so 0 KL divergence. So so in summary, the thing is like that: if you keep all other qi except qj fixed, and you want to change your qj so that you get the best approximation to you get the highest value of LQ, your q will be nothing but some p curl over xz. Not I think I said p hat over pxz, the joint distribution over x, and only that part zz. So this should be equated. These two should be equated. All right, now let us, I have only given a property of p hat. Now let us look what p hat, okay, should I call it p hat? Anyway, I'm calling it p hat. P tilde rather, I think it should be called. All right, so we have said before that log of q star j is log of p hat j, which is equal to expectation of log of p x j. This should be log expectation of log of p of j over q, rest of the factors of q except j. So if you solve this, you will see this q star, this I can actually call it q star j, and note that it is a function, it's a is that particular factor restricted to this part of z. It turns out to be, if you just solve this equation, exponential e to the power this expectation with respect to the distribution of the rest of the factors of q except the jth factor. This distribution divided by some normalizing constant. Divided by some normalizing constant. Okay, so in summary, what we will do, we'll just cycle through a set of steps. So first, what we will do is that we'll start. You remember our q. I want to find out q, our approximating distribution. We say it is q1, q2 up to qa. We'll start with q1, and for each of these, I'll have some initializations, some initial guess of q1, q2, qa. And then I will update, and what I have is that this joint distribution p of xz, z was theta, it would be px theta. This we have, this is known. This is the product of the likelihood x given z into pz, the prior pz. So this is known, this is given to us. The problem was with the posterior. This is given to us. So all we do is that we, in the first step, we fix all this and update q1 using this formula. What does the formula say? It says that you take expectation of log of this quantity with respect to the rest of the distributions that you are keeping fixed. With respect to the rest of the list and raising it to the power e. So this is my new value of q1. And this is the optimal value of q1 in the sense that we have already shown that this maximizes the ELBO. This maximizes the ELBO if everything else is fixed. Now cycle. Now keep q1, new value of q1 to be constant. Now look at q2. And now update q2 again using this formula, but this time you take the expectation of pxj with respect to only this, the remaining, and update q2. And similarly update ql and repeat the entire thing till the ELBO value converges. We can actually prove that this will always converge. Using the similar arguments that we studied in normal Bayesian variational Bayes, that you always go to a higher value. There is always you always go to a higher value of the ELBO at every iteration. Okay. In general, this expectation is numerically computed. So it's an expectation. So in practice, you don't need to do this integration. You need to do a summation over the variables, and this is just a summation over the data points. Maybe computationally difficult, still very difficult. There are modern approximations which reduce this computation for big data, but for moderately sized data, this is manageable. Okay, so in worst case, you do numerical, but if there is a conjugacy, okay, if there is a conjugacy, something known as local conjugacy, that means if you have a conjugacy, so keeping all these Q fixed, if you just look at, so you remember the priors were, prior actually is this thing. Okay, so if it is so that given rest of the rest of the latent variables to be constant, if you look at this conditional prior, if this conditional prior and this particular Q1 in, or let us Qj, this and this final Q star j, if they have the same functional form, we say it to be locally conjugate. Note that this full distribution Z1 to Zm and the full distribution Q Z1 to Zm, they need not be conjugates. Well, why are you talking of conjugate? Because this is kind of approximation to the posterior. Normally we talk of conjugate if the posterior in the prior are of the same functional form. But we replace the posterior here by Q because Q is the approximation to the posterior. And in general, we would call it a full conjugate if Q and P overall Z1 to Zm have the same form. But that may not be the case, but instead we can have P of a part, P of only a part of the prior, that means only the J part, that might be a conjugate to that particular part of the approximation of the posterior. Okay, these two may be conjugate, even though these two are not conjugate. So this is called the local conjugacy or conditional conjugacy. Local conjugacy or conditional conjugacy. So we'll soon see an example of this. And if local conjugacy is there, then this expression for Qz, becomes a closed form expression, becomes an analytical expression, a closed form expression. And then, so if it is a closed form expression, then update is very fast. But if it is not, do this. Okay, so let me summarize. So actually, I'd like to mention, in fact, what is done is that usually this Q is directly not updated. Instead, log of Q is updated. This is removed, log of Q is updated, and this is a constant. Okay, so usually the update is log of Q star j is expectation of log of Q. So you calculate this expectation and say, and then you update log of z, log of Qz rather than Q. Okay, so the summary, this is called the coordinate, rather the block coordinate ascent variational inference, a practical algorithm. You assume, so what you, okay, one more thing is that, so after these updates, you will find the value of Q1 up to Qm. And we know the entire Q is product of this thing. So fact, these are just the factors, is the product of this thing. So if you know Q1 to Qm, you can find the full Q. Okay, so cavi is this. You for each j equal to 1 to m, the value of Qz is updated as the e to the power expectation of log of px. Note that this is known. This is known. Where the expectation is taken over the rest of the parts of Q, rest of the factors of Q except j, and this raised to the power e gives the new Q. Okay, and you iterate. Now you change your j and again do this thing. And after each step, compute your ELBO. Because now you, whatever Q you have by the product of all these Qj's, use that, compute this. And when ELBO converges, doesn't change much, you stop. Okay, so what type of approximation we get by this? So I have already discussed, if you have kind of a skewed or very elongated kind of distribution, then this, if you have a nice circular distribution, the original distribution P is nice circular, then you get a very nice thing. But if it is, say, something elongated like this, then this is the kind of approximation you would get by VB. If the original P is multimodal, then this VB creates a problem. It's some kind of a mode collapse issue. So it locks into, note that the convergence rule of this variational Bayes or the mean field approximation says that you get a local maxima. It's not necessarily you get the global maxima. So what happens is that if you have a multimodal distribution, the local maxima locks on into one of the modes. It locks on into one of the modes. Okay, so let us quickly take an example to solve this. What is a factorized distribution? Well, this example is kind of really constructed one, because we actually don't need approximate inference for this case. But nevertheless, let us take it. So we have data points x1 to xn, and each of x1 to xn are scalars, univariates. The likelihood function is Gaussian. This is the likelihood function. It is Gaussian with mean mu and variance 1 minus tau. Okay, which we call precision, variance 1 minus tau. And so there are two parameters, mu and tau. Tau is 1 by sigma. Okay, so we have two priors now. We have two parameters now, mu and tau. So that is our theta, z, or whatever you call. There is no z here, so it's theta. If we take a Gaussian mixer model, instead of a single Gaussian, there would be a latent variable z, which is the cluster number. Okay, so let us see the joint distribution, the prior, which is P, mu, and tau. We say it is the product of two distributions, P mu given t, sorry, mu given tau into P tau. And just this by the definition of the joint distribution, P mu, or rather the definition of conditional probability. So it is P mu, mu given tau into P tau. So you see, this is kind of a product. This is kind of a product. This is kind of a factorization of P theta. It's kind of a factorization of P theta. And for P mu given t, we assume to be a Gaussian with mean mu naught and variance, or if we talk about the inverse of variance, it is some lambda naught into the tau of the original distribution t. This is my sigma. So this is one part. And the second part, that is P tau, is a gamma distribution with parameters a naught, b naught. Okay, so this is called a normal gamma prior. Normal gamma prior, and so this is my prior. This is my prior, and this is my likelihood. If you multiply them and take the evidence in the denominator, in this case, it turns out to be closed form, because this normal gamma prior and the posterior, they are conjugates. And if you actually work out, you will get that the posterior is actually a normal gamma. Posterior will also be a normal gamma, because as you know, this is a conjugate. That means the prior and the posterior will have the same distribution. So the prior is normal gamma, posterior will also be normal gamma. But anyway, let us try to make an mean field approximation of this. So let us assume that we want to approximate the posterior. What is the posterior? Posterior is mu tau given x. We want to approximate this posterior by some q mu tau, and q is a mean field approximation. That means I can factorize q into two parts. First part I called Q mu, which is Q1 basically, and Q tau, which is Q2 basically. Okay, so if we look at the CAVI, that is coordinate ascent variational inference rule that we derived here, if we look at these rules, we will see that log of Q mu, this is the update rule for the first part, is expectation with respect to Q tau. Remember, log of Q mu is with respect to, for Q1 you use the expectation with Q2, and for Q2 we'll use the expectation with Q1. So expectation with respect to Q tau, the joint distribution between X and mu and tau, plus some constant, which we have already seen that this is the normalizing constant, but it's constant with respect to Q. So this is Q star by CAVI, and this is similarly Q star tau by CAVI. Okay, let us look at the joint distribution. So the log of this joint distribution, this quantity, if we apply all these the assumptions that you have used for the likelihood and the prior, we'll see that it is, this is the likelihood. The log of the joint is log of the individual parts. So it is log of the likelihood plus log of the two parts of the prior. Prior we said that is a factor of, it's a gamma normal, it's gamma into normal. Okay, so this is the log of the joint, log joint. So now if I apply this, because we are Q star mu is only the mu part. So if you keep only the mu part, and if you take the expectation with Q tau, this will become this, because this is independent of mu. This is independent of mu. So log of Q star would be this. Log of Q star would be log of the joint. So sorry, log of the conditional plus log of the normal part of the prior. Log of the normal part of the prior. This part of the prior. This part of the prior. Okay, and this is if we assume all the examples x1 to xn are IID, then this likelihood gets the product of independent assumption, product of all the individual data points. So you get, if you substitute this here, it's log of this thing, and since this is Gaussian, you take the log of that, you get this, and since this is also Gaussian, you take the log of this, you get this. So your log Q star would be the expectation of this quantity plus a constant, and you have to take the expectation of this quantity with respect to Q tau. Okay, and Q tau, we already know the form of Q tau. We already know the form of Q tau. You can easily verify that if this holds for Q star, this holds for Q star, then Q star is also a Gaussian. You can naturally see. So log of this is linear. So this has to be a e to the power something, which is a Gaussian. So this I'm not working out. If you work out, you'll see that Q star mu is also a Gaussian. Note that we are having this closed form of Q star only because they are locally conjugate. If not, we could not have had it. So it will be a Gaussian with mu n and tau n parameters, where mu n is something like this. So it is a parameter. It's the data part, the mean of the data, the sufficient statistics for the data, plus the prior parameters, and divided by this. And similarly here. Okay, so this is exactly same as the log gamma full Bayesian that we did earlier. So the approximation is exactly same as the full Bayesian, but in general that will not be the case. Similarly, we can show, if you go ahead, this is for Q mu. If you go for Q tau, Q star tau would be turn out to be gamma distribution. Again, this is a kind of a conjugate, because the posterior and the approximate to the posterior and the prior is both are gamma, with parameters a and bn, where a and bn can be shown derived to be of this particular form. Okay. But note that the update on Q star and Q tau, they are kind of, there is a cross link between them. The update on Q star requires knowledge of Q tau. Similarly, update of Q tau requires knowledge of Q star. Okay, they depend on each other, and you circulate circle between these two. And if you keep on doing this, you will get into a convergence, and that will be, in this case, actually the approximate solution will be very close, because the posterior in this case is also a factor form. So it's the mean field approximation is not really an approximation. So, but in general, it will be an approximation. All distributions cannot be factorized. Let us look at some pictures, what actually will happen. So if we look at the posterior p mu tau given x, so it's a bivariate distribution over mu and tau, and this green line is the actual p which you are trying to optimize, and these blue contours are q's that are approximators, factorized mean field approximations. So this is where you start from, and after you solve the first step, that is q mu, you find out, you will see that q mu, as I have said before, will be some distribution like this. You will try to approximate the mu axis. And then once q star mu is found out, keep that as fixed, find q star tau. Now it will try to approximate the tau direction also. Okay, and now we will after first update we will get, so first update what it does is just shifts it and spreads it along x direction, and the second update, this one, it takes and spread it along the y direction, and maybe move the mean a little bit. So it's get this, and if you do this for several iterations, you will see that the final q, if we run for infinity, they will exactly be the same, because in this case the p lies inside script q. In general, that will not be the case, but if after a certain number of iterations, this will be a very nice approximation. All right, so this is what I told, that this is an example of a locally conjugate models where you get a closed form, but in other cases also you can do. All exponential families, the gamma, the Gaussian, and the other, Weissart and the other, they are all locally conjugate. So for all of them, the mean field approximation has a closed form, the q star has a closed form expression. Okay, in general, there are, so this is the Kavi coordinate ascent. People have tried to minimize the ELBO by not just Kavi, but also by general gradient descent. So you basically take the gradient of ELBO. You take the gradient of ELBO, known as ELBO gradient, and just since this is objective function over all possible q, you take the gradient descent. So one of the simple way you can do this is that if you can parameterize q by some parameter phi. Yeah, all the, for example, here the q is parameterized by these parameters of this alpha naught, mu naught, all these are parameters. So if you can parameterize, sometimes you cannot. If you can parameterize, then it's just a gradient descent over alpha naught, beta naught, tau naught, and all those things. It's just a gradient descent. You can take the gradient of ELBO and do it. This you can solve even if there is no local conjugate. So of course, normal VI also you can solve if there is no conjugate. You just need to compute a expectation. Okay, so this is also a popular method that is more common nowadays than Kavi. What people actually do, I'll tell you, instead of assuming some form of this joint distribution or from some form of the prior, and you take the expectation over this, people replace these quantities by a deep neural network, and this QZ also by a deep neural network. Okay, so these distributions are not a algebraic form, they are a neural network. And if it is gradient descent, then what you do, it is basically a gradient descent over the neural network weights, because now the parameters of P and Q are not alpha not beta not, they are weights of the neural network. Okay, so they do a gradient descent over the neural network. So basically it becomes a neural network training technique where the objective function is not mean square error, it's the ELBO. Okay, it boils down to that. So there is a big group of method called Bayes deep learning, Bayesian deep learning, or deep Bayes. So they basically combine. See, these Bayesian methods, they are kind of broad inferencing principles. What probabilities you use, what uncertainties do you use. They do not talk much about the model. So that is Gaussian, or okay, Gaussian is very important, but gamma or something. So you can do all this Bayesian analysis if you replace this Gaussian or gamma by neural networks. You just, instead of taking a very well-known popular distribution, you have neural networks for them. They are also produce distributions in the output, random variables in the output. So this gives rise to a big area called deep Bayes, because normal deep learning has a problem that you cannot interpret the output as a probability or uncertainty or something. But if you put in this Bayes layer in front of deep learning, you can as well interpret them in terms of probabilities, uncertainties, and so on, which are useful in practice. Okay, so finally, if you write a program and run this Cavie algorithm or the gradient descent, whatever, you will see that there is a, just like neural networks, there is a local minima convergence problem. They saturate, but sometimes they get stuck in a local minima. So initialization of how to start with the initial values of Q1, Q2, Qm. But initialization does have an important role on the convergence results. Finally, the modern research is more into more general cases. Like I said, neural network, you don't need locally conjugate models. You don't need mean field factorizing assumptions. And the second is, all this Cavie requires an expectation computation, which is basically a summation, which is costly for big data. So can we have scalable forms of this? Can you do Cavie very fast? Okay. In general, people now more, instead of all these mean field approximation and conjugacy assumptions, people do not make any model specific derivation. They just write the, but ELBO is still there. They take a gradient of ELBO and just they do a perceptron like update, just a gradient descent update. Okay, where you can take the gradient of the ELBO, gradient of expectation. How to do this scalably? How to do this for large data? Sometimes this happens that this gradient of the exponent is easier to compute than the exponent. Gradient of the expectation is easier to compute than the expectation. Directly you can compute without computing the expectation. So and how to do it scalably for large data? These are the motivations. These are the modern research directions. It's still very popular. Okay, so I stop here, and I'll give you upload. There are chapters of Kevin Murphy, and there are nice chapters in Bishop book on variational Bayes or variational inference. You can go through them. I'll upload the page numbers. You have any other doubt, you can ask me if you have any other doubt. Okay, otherwise I'll stop. Let me stop the recording.